Okay, so let's try to put together all this great knowledge we collected about warm air rising, cold air sinking, this cell that would formed, the convective cell that formed with the heater in a room, or the part of the sphere that we showed where warm air, low pressure, rising air hitting the tropopause and then sinking somewhere, high pressure, cold temperatures, and we had air coming into the low pressure region to replace the rising air, which we called convergence, and sinking air, high pressure, actually was diverging at the surface, and so on. So the circulation cells in the atmosphere in each hemisphere have this three-cell structure called the Hadley cell, which goes from about the equator to 30 degrees latitude, a Ferrel cell, obviously people associated with discovering these things, goes from 30 to 60 degrees latitude, polar cell, cold temperature, high pressure at the poles, which diverges air away from the poles between 60 and 90 degrees latitude. You have a rising air and descending air in these cells, which produce high and low pressure zones. And we will see, if you go to advanced stage of learning mathematical dynamics and so on, that this three-cell structure is kind of an idealized depiction. There are some complications or mathematical concepts involved in what happens if you move a parcel of air from the equator all the way to the pole. You have something called angular momentum, which becomes too large to continue, so the system breaks down and you have kind of instabilities and so on that some of you may end up learning later on. Okay, so the high pressure zones that are almost semi-permanent zones on a map that you can always find are called the subtropical highs, which are around 30 degrees latitude. One of the more popular subtropical high you may have heard of is the so-called Bermuda Triangle, which is part of one of the subtropical highs. You hear about ships disappearing and so on and so forth. And you have polar highs, cold temperatures, high pressures at the poles. We said warm air, low pressure is associated with rising air, which expands, the water in it condenses and it rains. So low pressure typically associated with bad weather, whereas sinking air is associated with good weather, clear skies, no rain. So also could be a desert. So good weather is not always a good thing if it is a permanent good weather, right? The low pressure zones, on the other hand, where the air rises, are the equatorial low and the subpolar low. So we have tropics, subtropics, temperate latitudes, subpolar latitudes, and polar latitudes, right? So you have subpolar lows, and you can remember the time we showed the evaporative zones in the subtropics and wetter zones or rainy zones in the subpolar latitudes where there are lows. We'll see that these make for interesting circulation patterns. So these low pressures, as I said, tend to have overcast skies with lots of precipitation. So the three-cell mode of atmospheric circulation looks like this. Looks complicated, but just listen to it, and then we will look at an animation with the seasonal cycle to understand how the system actually works. We have again simplified the situation here in terms of not showing the complications associated with having more land in the northern hemisphere, less land in the southern hemisphere, and the asymmetries. Remember when we made a zonal mean meridional section of rainfall, for example, we said the wettest region, the low salinity region, is not on the equator but it's slightly off the equator, and so on. So here we are almost thinking of something like an aqua planet where the entire planet is just covered with water and all the continents are submerged. Okay, so what happens? We have net energy being received in the tropics, as we said before, more short wave coming in than long wave being lost. So there is warm temperatures, which means low pressure, which means warm air rising, and we said air then has to converge into it to replace the rising air. And now you have to add your other bit of knowledge where you have Coriolis effect, right? So if you try to bring air from the poles towards this rising air, low pressure in the deep tropics, what would happen? In the northern hemisphere, you have this rightward tilting of the air by Coriolis. In the southern hemisphere, you have the leftward tilting of the air by Coriolis. So you can see that you end up with winds not directly converging from the north and south, but they end up coming from the northeast and the southeast, which end up being called trade winds. So you have rising air, which is going to hit the tropopause, the ceiling that we talked about between the troposphere and the stratosphere. And rising air means overcast skies, so low pressure, clouds, and rain. So that air, warm air that's rising, is hitting the ceiling in red arrows and going towards the poles. And again, you have to imagine in the upper atmosphere, Coriolis is going to keep moving it as it's trying to go north. It's going to get tilted to its right, which means the air going from the equator towards the north is going to turn towards the east, and in the southern hemisphere going towards the south, it's going to be also turned to the left, so towards the east. And that air loses its heat along the way, gets cold, and sinks around 30-degree latitude, as we said, and that's where you get high pressure because the sinking air is cold, and also it begins to get compressed. There is adiabatic compression and a little bit of warming and so on and so forth. But these regions have high pressure, clear skies, and no rain. These will be like the deserts of the ocean. When we look at primary production or the forests in the ocean, if you will, we will see that ocean also has deserts, and it's along these same latitudes where land also has deserts. There are additional complications because of how the land affects the Hadley Cell. So this Hadley Cell is essentially the air rising in the tropics, hitting the tropopause, going poleward, and sinking in the subtropics around 30-degree latitude. Again, the cells shown on the side are rising in the vertical, and you can think of them again as zonal mean meridional sections, even though we are showing the map in the middle. Okay, so Hadley cells in each hemisphere. Let's for the moment assume they are symmetric. And you have on the other side something that is not so intuitive. Okay, so if you jump to 60 north, we said that's the low pressure region where there is again wet weather, low pressure system. There you can see that warmer air is again rising and moving towards lower latitudes. It's again going to cool along the way, and it's going to meet this sinking air around 30-degree north. So how is it that you have air coming from colder latitudes towards warmer latitudes and rising in the colder latitudes with rain in the colder latitudes? Okay, this is where this detail of mathematical complications that we are not going to go into in this course, but you can understand it better this way. Let's jump to the poles. The poles are very cold, right? Snow and ice, Arctic ice over there, Antarctic glaciers in the southern hemisphere at the South Pole. Cold polar temperatures are going to have very high pressure, and every time you have a high pressure center, you have low pressure around it. So the air is going to move from the high pressure in the middle towards the low pressure all around, the divergence that we talked about. Immediately we're going to add Coriolis to it. So at the poles, if you see air coming towards the south, Coriolis is going to move it to the right of it, so it's going to go towards the west, right? So you end up with what are called polar easterlies. So you have sinking motion and high pressure at the poles. That air that is being pushed away from the pole, diverged away from the pole towards the lower latitudes, at some point is going to get warmed up and it's going to rise. So you're going to have this polar cell with sinking air over the pole, cold, high pressure, low rainfall, low precipitation. At high latitudes, precipitation is usually snow. So you have what is called a polar cell. and we had this Hadley cell in the tropics and subtropics. So what happens in the middle, the so-called polar cell between the Hadley cell and the polar cell, is kind of a kinematic cell. It's like a gear. You have a gear in the tropics and subtropics that is driven by warm temperatures in the tropics and low pressure and rising air, and you have the polar cell like a gear being driven by high pressure cold temperatures at the pole, pushing air out towards the low latitudes. And these two cells are being connected in the middle by a third gear, which is essentially the Ferrel cell, which has this counterintuitive circulation of rising air and low pressure at a higher latitude around 60 north, and a sinking air and colder air, high pressure at 30 degrees north. Absolute temperatures are still obviously going to be much higher at the subtropical high, where the air is sinking and deserts are forming, compared to the polar front. Nonetheless, the air is warm enough there and the pressure is low enough for it to rise. Okay, so technically speaking, these Hadley cells and polar cells are called thermally driven direct cells, which means there is a thermodynamic forcing because of cold temperature and high pressure, or warm temperatures and low pressures. And Ferrel cell is called a thermally indirect cell because it's just a kinematic gear that is linking the polar cell to the subtropical cell. Okay, so something to remember. Let's add a few more terminologies once we restart this podcast. Since it's got a few concepts that are not so straightforward, I'm going to stop this podcast here so you can watch it again and again. Make sure you understood the three cell structure. Just remember the three cell structure. Don't worry about the asymmetry and so on. Hadley cell, Ferrel cell, polar cell. Hadley cell and polar cell are the thermally direct cells, and Ferrel cell is the gear that is the thermally indirect cell.